Welcome, everyone. Today, we are going to explore one of the most fundamental challenges in systems programming, the memory management trilemma. This concept highlights the constant trade-off between control, safety, and simplicity. As we see on the slide, these three ideals are often in tension, and choosing one frequently requires compromising on another. On the left, we have the philosophy of control, exemplified by C. Represented here by the intricate blueprint of a mechanical device, C gives the programmer absolute power over every byte of memory. It is raw and efficient, but it places the entire burden of safety on the developer's shoulders. In the center, we have safety, the hallmark of Rust. Symbolized by the reinforced shield and padlock, Rust uses a sophisticated ownership and borrowing system to provide memory safety guarantees at compile time. It protects the developer from common pitfalls like null pointer dereferences or buffer overflows, though often at the cost of increased language complexity. Finally, on the right, we see the emergence of Zig, which champions simplicity and precision engineering. Zig avoids the hidden behaviors of other languages, opting for a transparent approach that feels like architectural design. It aims to provide the control of C with modern safety features, all while keeping the language simple enough for a single developer to hold the entire specification in their head. Over the next few minutes, we will dive deeper into how these three languages navigate this trilemma and what it means for the future of system-level development. The C approach to memory management is characterized by a philosophy of absolute power accompanied by absolute peril. By granting developers direct control through the use of malloc and free, the language provides maximum flexibility but lacks a fundamental safety net. The model itself is straightforward. You manually request memory and are then solely responsible for its eventual release. However, this total responsibility means that a single mistake can result in critical bugs. As shown in the diagram, mismanagement of the heap leads to common vulnerabilities, such as memory leaks, double freeze, and use after free errors. Because C provides the tools without the guardrails, it is often described as a legacy programming language prone to footguns and security holes. In this environment, the burden of ensuring memory safety falls entirely on the programmer's discipline rather than the language's design. Rust's fundamental solution to software safety is rooted in its compiler. By introducing a strict ownership model and a specialized component called the borrow checker, Rust is able to identify and prevent memory errors before a program is ever executed. As illustrated here, the compiler acts as a gatekeeper. Code that follows the rules of ownership and borrowing, represented by the green flow, passes through the borrow checker to become a compiled binary. Conversely, any code that risks memory safety, such as through data races or invalid references, is caught immediately, resulting in a compilation error. While this requires developers to work strictly within the compiler's confines, it provides a powerful guarantee. If the code compiles, it is memory safe. This approach eliminates the need for manual memory management or a runtime garbage collector, as memory is freed automatically the moment it goes out of scope. The Zig path represents a philosophy where manual management is made simple, safe, and transparent. Zig fundamentally rejects hidden control flow and hidden memory allocations, providing instead the tools necessary to make manual management both robust and clear. By charting this distinct course, Zig asserts that the programmer should always remain in total control, while proving that manual memory management does not have to be error-prone. The core philosophy is that explicit is better than implicit. Consequently, there is no garbage collector and no hidden allocations. Instead, Zig empowers developers with a powerful and flexible system of allocators, ensuring every operation is intentional and visible. One of Zig's core design principles is that there are no hidden allocations. To understand why this matters, let's compare it to how C handles memory. In the C example on the left, we see a function signature for repeat. While it returns a pointer to a string, it is not immediately obvious how that memory was allocated. It is generally assumed that malloc was used, which creates a hidden dependency on the standard library. Furthermore, the caller has to consult the documentation to know they are responsible for calling free later. Now look at the Zig implementation on the right. The repeat function explicitly requires a pointer to an allocator as its first argument. This makes it impossible to ignore the fact that an allocation is happening. Because the allocator is passed in, the caller maintains total control over the memory strategy, whether that involves using a heap allocator, a stack-based arena, or a fixed-size buffer. This design ensures that all memory dependencies are clear, deterministic, and visible directly in the function signature. The power of explicitness lies in providing developers with unparalleled clarity and control over their software. This starts with the elimination of hidden allocations. When a function signature requires an allocator to be passed in, it serves as an immediate signal that an allocation might occur, removing performance surprises and hidden costs. This leads directly into total strategy control. The caller, rather than the library, decides exactly how memory is managed. Whether you need a general-purpose allocator, a temporary arena for batch processing, or a fixed buffer for real-time constraints, the function works seamlessly with any of them. Furthermore, this design provides freedom from libc. Because the standard library is allocator-free internally, it is ideally suited for bare metal environments and custom allocation strategies, as it is never tied to a system allocator. By making allocator independence an explicit design goal, we ensure that you can dictate whatever strategy or constraints your project requires, while still utilizing the full power of the standard library. Zig's defer and error defer statements provide a mechanism for structured safety by guaranteeing that cleanup code runs when a scope is exited. This prevents common issues like resource leaks, which can be difficult to manage manually in languages like C. The defer statement ensures that cleanup logic, such as freeing memory or closing file handles, is executed no matter how a function exits. In this example, immediately after allocating memory and opening a file, we use defer to schedule the corresponding free and close operations. As shown by the arrows, these actions are automatically triggered when the function reaches its closing brace, or even if it returns early due to an error condition. In addition to defer, Zig offers error defer, which executes cleanup code only if the function exits with an error. This distinction makes writing robust and correct code much simpler, as it allows developers to handle resource management locally and predictably within any given scope. Zig's standard library provides several allocator implementations, each suited for different tasks. Think of them as specialized tools, each with its own philosophy. First, we have the general-purpose allocator, often referred to as the librarian. It is designed to track everything meticulously, making it an essential tool during development for detecting memory leaks and ensuring your program manages its resources correctly. Next is the arena allocator, which can be visualized as dumping Legos. This strategy is optimized for fast bulk allocation and cleanup. Instead of managing individual objects, you allocate what you need and then release the entire arena in one single operation, which is highly efficient for transient tasks or request-based architectures. The fixed buffer allocator is akin to a fixed-sized box. It operates within a pre-allocated memory buffer without ever touching the heap. This provides ultimate predictability and performance, making it the ideal choice for environments with strict memory constraints or real-time requirements. Finally, the page allocator is like buying land. It is used for requesting large, raw chunks of memory directly from the operating system in page-sized increments. While not intended for small, frequent allocations, it serves as the foundational layer upon which many other allocation strategies are built. The Allocator Toolkit categorizes memory management into two primary strategies, everyday and temporary. On the left, we have the General Purpose Allocator, or GPA. This operates much like a librarian, meticulously tracking individual books, or a toy box, where every single item must be returned to its specific spot. The GPA tracks every allocation individually, which allows it to detect memory leaks and double freeze during initialization. It is the preferred choice for general application development, where fine-grained control and robust error detection are essential requirements. Conversely, we have the Arena Allocator. Its workflow is comparable to dumping out a box of Legos to play and then sweeping them all back into the container at once. The Arena Allocator provides exceptionally fast allocations from a single large chunk of memory, and all that memory is freed simultaneously. This makes it ideal for temporary data that lives and dies together, such as when parsing a JSON file or managing the short-lived assets required for a single game frame. Selecting the right tool depends on whether your priority is individual tracking and safety or high-speed bulk management. In this section of the toolkit, we examine specialized and system-level allocators, beginning with the fixed buffer allocator. Conceptually, this acts like a fixed-sized box that never grows. It allocates memory from a predefined buffer, typically on the stack, and avoids heap allocations entirely. This tool is best for embedded systems and memory-constrained environments, where heap allocation is either forbidden or undesirable. Next, we have the page allocator, which is akin to buying a huge chunk of land directly from the government. It allocates memory in large, page-aligned blocks directly from the operating system. This is the ideal choice when you require large, raw chunks of memory to serve as a foundation for building other, more complex allocators on top of. Zig's explicit approach and allocator-free standard library result in dramatically smaller binaries compared to languages with mandatory runtimes. This data illustrates the practical payoff of a zero abstraction cost philosophy by comparing Zig to Rust across 3 common scenarios. For a simple web server incorporating JSON and SQLite, Zig produces a binary of only 850 kilobytes, while the Rust equivalent is nearly 5 times larger at 4.2 megabytes. This gap persists with a minimal HTTP server for Docker, where Zig requires just 300 kilobytes compared to Rust's 2 megabytes. Even for a basic static Hello World binary, Zig maintains its 300 kilobyte footprint, whereas Rust requires 1.8 megabytes. These results from pragmatic AI labs highlight the significant efficiency gains and reduced overhead that Zig provides for systems programming. Raw speed is where Zig truly shines, proving itself competitive with the most optimized languages. In this head-to-head scientific computing benchmark involving 1,000 runs of stochastic process generation, Zig's performance is on par with an optimized Rust implementation. While Rust's release build averaged approximately 2,828,673 nanoseconds, Zig's release fast build achieved a slightly better time of 2,819,137 nanoseconds. This margin is attributed to Zig's granular control over memory initialization. Specifically, by using the undefined keyword for stack memory allocation, the developer avoids the cost of zeroing out large chunks of memory for every iteration of a loop. This ability to skip unnecessary work is a primary driver behind Zig's elite performance profile. This slide addresses a fundamental design philosophy, the deliberate trade-off of clarity over conciseness. A common pain point often raised is the perceived cost to readability and maintainability when allocators must be passed explicitly throughout a codebase. It can feel burdensome when a deeply nested function requires a heap allocation, necessitating changes across the entire caller chain. However, as illustrated by the balance scale, this requirement is a conscious choice rather than an oversight. We prioritize explicitness and control over initial brevity. The intentional friction of passing an allocator forces the programmer to remain aware of and accountable for every single memory allocation. This approach favors long-term maintainability and performance transparency, ensuring that the hidden costs of memory management are made visible and manageable from the start. The Zig project is driven by a grand vision, the engineering of a world-class allocator. Our ambition extends beyond simply offering an alternative. We aim to lead the industry in performance. This journey is centered on an explicit and ambitious goal: for Zig's default general-purpose allocator to outperform the most established and highly optimized solutions in the industry. As documented in GitHub issue number 12,484, our objective is for stead.heap.default allocator to surpass the performance of glibmalloc, jmalloc, and memalloc. This represents the ultimate expression of Zig's core philosophy, providing the tools not only for total control, but for achieving best-in-class performance.